Okay, so we're doing a circuit analysis example here. We're going to use Kirchhoff's current law to solve this circuit. We have basic little circuit here, a 10 volt supply, a 5 volt supply, two 1 kilo ohm resistors. In fact, in order to make this a little more interesting, why don't we add in a third resistor, and we'll call this a 1K resistor. Now, one thing in our circuit is we want to set up the reference voltage, meaning the 0 volts. We want to determine where that 0 volts is, and so I want to say 0 volts is right here. That makes sense, maybe because we can say 0 volts here. There's a 10 volt difference there, so right here we know we're going to have 10 volts, and because we have 0 volts here, this is upside down power supply, which means that you're going from positive to negative. It means that this is 5 volts more negative. That means we have negative 5 volts at that point right there. Now with this resistor over here, I want to put that to the reference voltage. So I can either draw a line and connect those things over there, or I can just draw the ground symbol, and that's the same as drawing a line. That means that there is a line magically under the table or under the paper or something that connects this point to this point. Okay, now in this circuit I want to solve for all the currents. That's what we're looking for. So I'm going to draw the currents in here. If maybe first we can count them, we can see that there is going to be a current through here, a current through here, and a current through there. There's not a different current through there. This current that's here is the same all the way through that point until it comes to this node, and the same there, and all the way to there. Same thing. So there's 3 different currents in this thing. So we're going to label them. We'll label this one I1, and we have to determine which way the current's going. So if we draw our arrow this way, that means that we are assuming that across this resistor that it is more negative on this side, meaning that you're going to go from positive to negative across that resistor. Same thing over here. If we were to draw the arrow going up just like we did over there, that means that we were assuming that we were going from positive to negative, from more positive to more negative. When in fact we're probably going to see that since this is probably a positive voltage up here, that we're going to go from positive to negative this way, so we can draw our arrow that direction. The same thing here. I think we're going to go from positive to negative that way. I'm just guessing. I don't know that. If we get it wrong, it will come out in the math later, but let's just say that we do it this way. I1, I2, and I3. Alright, so let's solve for I1, I2, and I3. Now, what do we know about these things? Well, we can't just say that. We know that it's going to be the voltage drop across the resistance is going to give us the current. But do we know the voltage drop yet? The answer is no. We don't know what the voltage. We know what the voltage is here. It's 10 volts. Right? We already wrote 10 volts there. But we don't know what the voltage is right there because, well, we just haven't solved for that yet. Same thing here. We know that it's negative 5 volts, but here we don't know what it is. So we have to solve for it. And because this is all one wire, that's all one and the same voltage. Again, we don't know that voltage, so we don't know what the voltage drop is here, so we can't find that current. So we know that we're going to have to solve for this current. I'm going to call it Vn. So we have to solve for that as well. Now, in order to do this, we also need to use Kirchhoff's current law, because we're going to have 4 different variables, I1, I2, I3, and Vn, and we can set up 4 different equations to solve for those 4 variables. So the first equation is going to be just Kirchhoff's current law. So we're going to say the currents into this node, we'd write all on one side of the equation. There's one current going into this node. The currents coming out of this node, we write on the other side of this equation. So we have I1 equals I2 plus I3. So that's the first equation, easy. The second equation, we can solve for I1. We can say that we know what I1 is going to be because it is going to be 10 going this direction, 10 minus Vn. 10 minus Vn and that's over 1k. I2 we can solve for. Now we have, let's move that wire out of the way. We have Vn, we're going this direction, so it's not minus 5 minus Vn. What it is Vn minus negative 5. So we have Vn minus negative 5. And that's going to be over 1k. And then we have I3. And we're going to have Vn divided by 1k. We could also, to be explicit here, we could say Vn on this side, 0 on that side, Vn minus 0 over 1k. And now we have 4 equations and 4 unknowns, and the rest is just algebra. So what I'm going to do is I'm going to take all of these and plug it into this first equation, to Kirchhoff's current law. I'm going to say 10 minus Vn over 1k is equal to En, I just combine those, and so we have plus 5 over 1k plus Vn over 1k. Let's get another sheet of paper. The first thing that I see to do is get rid of all the 1k's, divide both sides by 1k, and you're left with 10 minus Vn is equal to Vn plus 5 plus Vn. So I'm going to take this Vn over here and this 5 over here, so you have 10 minus 5 equals Vn plus Vn plus Vn. And so you have 5 equals 3 Vn. And so the Vn is just 5/3. Which is 1.6 volts. Alright, so now we can go back up here. We can look at our circuit again. We can see that Vn up here is equal to 1.6 volts. So now we know the voltage on this side and the voltage on this side. We have 10 minus 1.6 divided by 1k. And 1.6 minus negative 5 divided by 1k, and 1.6 divided by 1k. And we have those same equations right here, so we can go back and plug those values in, and why don't we just do that? So we're going to solve I1, and it was just equal to 10 minus Vn over 1k. 10 minus 1.6 divided by 1k. And that's going to be equal to 8.4 milliamps. I2 equals Vn 1.6 minus a negative 5 divided by 1k, and so that just equals 6.6 milliamps. And then finally, I3 will equal 1.6 divided by 1k, and that just equals 1.6 milliamps. And you see that we're off by a little bit of a rounding error, because if we were to plug those back in and we were to say I1 8.4 equals 6.6 plus 1.6, you can see, because I dropped off the 666 on both of those, that we end up a little bit off, because this is going to be 8.2 instead of 8.4, but that's just a rounding error. If you work these things properly, then you get exactly the right answer, but that's just a rounding error. At any rate, that's how you solve one of these circuits.